Sometimes it can be pretty obvious that what someone wants and what someone gets can be quite different, just as the cost and what they can afford can be quite different. And this is the essence of supply and demand, which usually starts at an examination of the demand curve. You can always tell the demand curve because the price is associated with a lower quantity. You don't want as much when it's more expensive, and vice versa. And the supply curve goes the other direction, where a higher price motivates marginal activities, products, equipment, employees, and vice versa. If the price is low, well, it's just not worth opening the door. And we can put the two over each other. And I might note it to my engineering friends that notice here we have price on the left and quantity across downstairs. And I would offer to you maybe flipping those in your mind for those of you who think in terms of mathematical functions. But in terms of the graph is unchanged. So let's proceed anyhow. And this is just about where it stops for most introductory economic analysis, in that we just see the demand and the supply lines, the curves, if you will, and we call this the Marshallian Cross, after a guy named Marshall who first thought of it. And sometimes the analysis goes on a bit more, where the demand, if it's below the supply price offered, or if the supply price is just too darn much, that nothing happens, there's no sales, there's no activity, and everything happens to the left in terms of quantity, in terms of actual sales occurring, a demand met, and a supply filled. At this point, sometimes depending on the color of the textbook, there may be a discussion of the law of one price. Here's three different colored price paths. And notice that each one of these indicate a person is better off. Each one of them bought it at a price that was below or sold it at a price above what they were willing to do. And that if there were entrepreneurs, arbitrageurs, or if you just did your own hunting, you probably could find a better price. And these all tend to converge where they cross each other. And that's the law of one price. But like a University of Columbia study, I bet you could think of some exceptions, like car sales, stereo, jewelry, big ticket items, and so on. Well, be that as it may, let's start with a very simple example. This is actually too simple, as we will see. And let's say we have a demand curve where each time the price goes up by $1, the quantity sold goes down by 1 unit. And let's say this firm has a variable cost of $4 and a fixed cost of, say, 0, because you're operating out of your parents' basement. And you certainly want to have your price above $4, because you'll notice anything below that, you lose money. And then someone might say, well, especially if they're a salesman, let's maximize sales revenue. And they would choose the price of $5, making a maximum revenue of $25. But that's not right, is it? Look at the profits. Profits is revenue minus cost, which is to say price times quantity, minus variable cost times quantity, minus fixed cost, which happen to be here, 0. And you'll find that the only way that has a relevant impact is to whether or not you open the doors at all. And putting these side by side, you can see, boy, there's a clear difference. At $7 we maximize profits, but at $5 we maximize revenue, and at $4 we break even. And if one wants to be fair to the economists, which is another question entirely, they might examine what's called the marginal revenue. That's how many more bucks you get for each unit sold. And their totem is that when marginal revenue equals marginal costs, profits are maximized, and we'll see that's true here, that the additional gain from 5 to 3, oops, we just crossed our marginal costs, and their profits were maximized. And this exercise of marginal revenue equals marginal cost, which is to say variable cost here, is that the naive street vendor, and not all street vendors are naive, and nor are all brick and mortar smart, is that if you raise or lower a price and you get more marginal revenue than your marginal cost, let's continue more in that direction, and vice versa. However, the version I used was not a curve by any means. And they do call it a demand curve for a reason. And here's a demand that is curved, and sure enough, the price is high and the quantity's low, and vice versa. And this one's now well behaved. You can kind of push it to the extremities. And notice we're not going to put a supply curve here, but we do have the common sense to charge above the variable cost. The idea here is the supplier moves along the demand curve, picking the sweet spot, the one that produces the greatest profit. Not a supply curve as such, because the person will just supply the amount that is demanded that maximizes profit. And this analysis, if in words, would come to a grinding halt or one of those long tomes, or we can look at some pretty spiffy mathematics using some calculus. Profits, again, revenue minus cost. Revenue is price times quantity. Costs are variable times the quantity minus the fixed. And we now need to describe a demand function that's well behaved, which means it can't cross the price or quantity axis. No intercepts. And here's one, have some scaling factor, let's call it K again, divided by the price to the nth power. And it can be shown that that power is the elasticity of the price. And this demand function can be substituted in for quantity in the profit equation. And I've labeled profit pi here for a couple of punny reasons. And let's see, our old friend, the first derivative with respect to price, can maximize the profits if we set that equal to 0. So let's do so. Solve for price, and we get P star maximizes profits. I should note that the elasticity is calculated as a positive number, just as the duration for bonds and interest rate risk is calculated for much the same reasons as a positive number, because we know that the relationship is always negative. So in any case, using that, we'll multiply that times the variable cost, and then divide that by the elasticity again, minus 1. Let's look at an example. Here we have variable costs of, let's say, 10, and we have two different prices. This might be a marketing experiment. The street vendor can certainly do this. Prices are 21 and 19, a price lowering of 2, let's say, and the quantity rose by 1,000 from 3,500 to 4,500. And we've calculated the revenues and the variable costs. Oh, heck, you can do that. And the profit. Hey, it looks like we should lower the price, but how much more? Let's calculate the elasticity. So we calculate the differences. Now to calculate the elasticity, what's called the arc elastic measure, so there's no bias from the base from which way you're moving. And interestingly, in finance, that presents the question of convexity, but not here. And let's see, the average prices was 20, and the average quantities was 4,000. So we take the proportional change in the quantity over the proportional change in the price, and that's a quarter divided by 10%, which is 2.5 to 1. And plug that into our P star equation, and we get a profit maximizing price of 16 and 67 cents. And sure enough, we wanted to lower the price in this example. Now I like to do this one for my students. What would the optimal coupon be for you marketeers? Well, people who collect coupons probably are more sensitive, higher elasticity. Their optimal price would be 15, so our coupon would be, yeah, that's right, $1.33 or something close. This is pretty good stuff. Dr. C invests.